Hello, my name is Taylor Harris and I am a security engineer with Charter Communications. Since 2010, I've been working in very large networks and I've been attempting to solve various security challenges in those large networks since 2013. DDoS mitigation has been a huge part of my time in the industry, so today I'm going to talk a little bit about how we can hopefully enhance DDoS protection collectively. So first, I think it's important that we briefly understand the evolution of DDoS and how DDoS mitigation is performed at the MSO level. After a quick review, we'll look at the most common reactive and proactive mitigation techniques, followed up by some of the challenges that we face using these strategies. Next, we'll dive into BGP Flowspec and how the protocol can be used to address some of those challenges. And then finally, we have a recorded demo of our homebrew auto Flowspec mitigation script. So, sometimes evolution sucks. As you may be aware, years ago launching a DDoS attack wasn't exactly an easy thing to do. Now if you know how to use a search engine, you can launch an attack. In general, we see an increase in the average size, the number, and complexity of DDoS attacks year over year. And now the vast majority of DDoS attacks that we see are directed at the home user. A lot of that seems to be related to online gaming. Next, most common targets are schools, typically during the standardized testing, and followed up by government financial institutions. So most of the DDoS traffic that we see originates from outside of the United States. China, Russia, Ukraine, just to name a few of the most common sources. Again, the attacks tend to keep growing each year, and I think for that we can thank the commercialization of DDoS as a service. So there's so many booter and stressor services out there that for a small fee will launch an attack to anywhere on the planet. But recently we've been seeing free DDoS services emerging in the market. Some of those will guarantee hundreds of gigabits per second of DDoS traffic. So there are two common methods for DDoS detection and mitigation. The inline solution places an intelligent device in line with the edge of a network, and this architecture is typically the most effective at dealing with and mitigating all different types of attack traffic. But there's a catch. So for MSOs, this can be an incredibly expensive endeavor, and as the inline device needs to scale not only to the network capacity, but has to be placed at each and every single peering location in the network. So when a network adds terabits of capacity each year and has dozens of peering points, it starts to become quite clear why this solution is not always selected as the first, from a CapEx and OpEx perspective specifically. So the most commonly used architecture is the traffic diversion method, also called the off-ramp method. This solution uses sampled traffic like NetFlow for the detection of an attack, and then it uses route injection to divert traffic to a single host, or for a single host rather, into a scrubbing appliance. That appliance will then have the intelligence to drop all of the bad traffic and hopefully forward along the clean traffic to its intended destination. There's many nuances in how re-injection and redirection are accomplished, so I'm going to keep it kind of high level so we don't have to worry about that. So here's the high-level network diagram. In this example, you can see we have a few core routers, we have two internet peering points, we have a scrubbing center, and we have our victim host. The collectors are constantly gathering NetFlow information from those peering routers. So our host is browsing the internet, playing an online game, something of that nature, and the legitimate traffic you see here in green. Suddenly, a flood of DDoS traffic hits that customer. Now, this is reactive, so we're waiting for the net flows to come in before we can engage on this. Once that sample traffic is analyzed, and this is determined to be a DDoS attack, the mitigation is triggered and all of the traffic destined to that one host is diverted into a scrubbing center, where hopefully we clean that traffic and pump the rest of the traffic that's clean down to the host. So what about being proactive? Well, one of the things we can do proactively is block and rate limit certain ports and protocols that are used in amplification style attacks. Blocking traffic ingress like charge-end, quote of the day, SSDP, RIP version 1, this is something we should all be doing. If you have a network and you are not blocking these protocols, please do. We also heard an earlier presentation this week about a new attack vector with port 11211, the memcache D. That was recently added to this list as well. And I believe it may also be time to start having the discussion about blocking ingress UDP source port 53, since this is heavily used in amplification attacks. For things that we can't drop outright, we can rate limit them. UDP fragments, SunRPC, SNMP, LDAP. These can be rate limited. We saw a good example earlier this week of a configuration for rate limiting down to 1% of the interface total. In general, you're only going to see impact on these services during a very large DDoS attack if you're leveraging rate limiting on those interfaces. But it could also help prevent some of that traffic, at least from transiting the network. We also heard this week about BCP 38. BCP 38 and BCP 84 define methods for blocking spoofed traffic, or rather denying spoofed traffic. These should be deployed ingress on every internet link. I think in North America we're pretty good about doing this, but remember, most of the DDoS traffic is actually originating from outside of the US, so it's really important that everyone uses these best current practices. The other proactive solution is an always-on mitigation, and essentially this solution would have a single /32 IP being diverted to a scrubbing center constantly, always having the countermeasures applied to it, whether there's an active DDoS or not. This method will still typically require some form of human intervention if a new attack vector or non-standard port's being used in an attack. Speaking of new attack vectors, these are always a challenge in security. One of the recent challenges we've had is an attack vector called the carpet bomb. It's not really a new attack. It's something that was seen some number of years ago, but a recent uptick in frequency does suggest that it may be becoming more popular. So what's different about the carpet bomb is, well, it leverages a normal UDP reflection or amplification style attack, but instead of having just a single /32 IP for the destination, it's many hosts, greater than a /23, like a /16 maybe, 65,000 plus addresses. So the victim is likely one of those 65,000 hosts in the attack. And supposedly the intention behind this attack is to destabilize the infrastructure that actually supports the victim itself. So to a normal host, you see, this doesn't look like a DDoS attack. This is 1 meg, 2 megs of traffic, but to a router where this subnet lives, it's no different than a standard volumetric attack. It can be 300, 400 gig. The difference is our typical detection and mitigation strategies don't work here. So this brings up a few important questions. First, can we advertise that many individual host routes for a redirection? That's not a good idea. Let's say we advertise the whole block that's under attack. If we redirect a /16, first of all, is that going to be the most preferred route? Probably not. Are we going to be able to take that much capacity at our scrubbing center? That's another big question. So the carpet bomb attack just goes to show that it's not necessarily the size of the DDoS that matters, it's how you use it. So how can we block traffic closer to the source? Well, BGP Flowspec might have some of those answers, right? We've seen a lot of talks this week about BGP Flowspec, and I know a lot of you are familiar with the BGP protocol. So Flowspec leverages the BGP protocol, and it allows us to programmatically and rapidly install access control lists on a router. It provides the flexibility to match very specific traffic types and to perform an action on that traffic, such as to pass, drop, rate limit, or set the next hop. And we can do this at the very edge of our network at line rate. So Flowspec is not without its own risks. The major one being the risk to router stability. Since each Flowspec rule requires a bit of memory in the router, every rule you send brings it closer and closer to the maximum. For this reason, very strong policy and process controls need to be in place. That will prevent overutilization. Reporting functionality is also something that's not built into Flowspec, so it does become a bit of a pain to gather metrics, and we know executives love metrics. So this isn't something that's really a con of the protocol, it's more of an observation. And I think it's something that the community at large can hopefully address in the future. Now let's look back at this high-level network overview. We can see our host again is browsing the internet, playing online games. This time, an attack occurs, but we have Flowspec mitigation. The countermeasures are applied at the very edge of the network, and the bad traffic is stopped, hopefully. If the attack was more complex, we could use the set next hop feature to redirect maybe some of the traffic, maybe all UDP traffic. And if it gets really bad and all else fails, we can use that same set next hop feature to redirect all of the traffic to a scrubbing center. Now, at least at this point, we have less bad traffic going in through our network and transiting. Another way that Flowspec is being leveraged in the industry is with regards to DDoS peering. Now, I genuinely believe that the only way we can eliminate DDoS on the internet is a collaborative approach with everybody. And to me, DDoS peering is the future of DDoS prevention. But it requires participation from as many as possible to be effective. So there's a previous talk at NANOG 71, CenturyLink and AT&T did a talk on DDoS peering. It was very good, we should check that out. But in short, DDoS peering allows for Flowspec rules to be sent from peers in an effort to block traffic as close to the origin as possible. So there's some really big risks, of course, and it requires incredibly tight controls again. But in addition to stopping traffic inbound, these rules can be used to prevent customers from sending DDoS traffic outbound as well. So in the graphic below, we see a DDoS attack that's marked in red coming through ISP-A in through ISP-B, and it's hitting that host. The mitigation rule, or the Flowspec rule, would be sent from ISP-B into ISP-A and saying, hey, block this traffic for us, and that rule would be installed at the very edge of ISP-A's network. In another scenario, we have this customer sending some outbound DDoS traffic from ISP-B, and ISP-A says, hey, install that Flowspec rule and block this traffic. And once again, we stop the traffic at the very edge of the network. All right. So a small group of individuals at Charter Communications worked together to develop an auto mitigation solution using Flowspec. This solution starts with a controller. The controller is written in Python, and here's how it works. So first, the controller listens for a syslog message coming in from the DDoS detection platform. Once that message is received, it looks for keywords in the message, identifies if this is a legitimate attack, and if it's one that we want to engage on and send these Flowspec rules for. And if it is a valid start message, we input that data into a SQL database, and it stores relevant information about the attack, such as being an active attack. Next, the Flowspec rules are sent to the exa-bgp API, and exa-bgp sends the Flowspec routes to a route reflector, and that route reflector then forwards all of those rules out to the appropriate routers. For each of these mitigations, here are the rules that we push. So right off the bat, rate limit UDP source port 53 to 30 kilobits per second. Same with TCP SYN, same with UDP fragments. Oh, I'm sorry, drop all UDP fragments. And drop UDP source 53 and destination 444, as well as other common volumetric UDP source ports, SNMP RIP version 1, TFTP, memcache D. And then finally, we rate limit all the rest of the traffic down to 100 megs per second. So once the attack is over, we're listening for a syslog message to identify that the attack has been ended. Once that message is received, we set the attack as inactive in the database, and this triggers the message to exa-bgp to withdraw the Flowspec rules. In case we miss a syslog stop message, there's a cron job that runs every hour, and it checks for any active entry that's older than 6 hours, and if so, it withdraws those rules as well. All right. We're going to look at the recorded demo next. Before we begin, I would like to give a shout out to the authors of this solution, Pratik Lotia, Tom Bowlby, and Rich Compton. So I'm not exactly sure how to start the video. Maybe they can start it for me. Perfect. All right, so as the video starts, we're tailing a log on the controller. We hop over to the victim, in this case, virtual machine, and we look at the nload command to show the incoming and outgoing traffic utilization. So you can see the device IP ending in .226 there at the top. Next, we move over to the attacker, and to simulate the attack, we use hping, UDP flood with the source port 11211, and we randomize the source IPs so that it looks like a legitimate attack. Now back over on the victim, we can see our utilization has climbed up to over 500 megs per second. This is not a very large DDoS attack, but it's big enough for the simulation to work. Back on the controller now, we wait a few seconds for this syslog message to appear. There it is. So we see that our host IP .226 is in there, we see the UDP signature, and we see that this is a valid DDoS attack, and we've started announcing the Flowspec rules. Back over on the victim, you can see the traffic has ceased, and now we look at the route reflector. These are the rules that we've pushed for that host IP. And then finally, we pop over to the peering router, and we see those same rules populated in the router itself. We also see the counters as they appear in there. The formatting is a little bit off because it's a very long Flowspec rule, but you can kind of see that those counters are rapidly increasing at this point. Back again at the Flowspec controller, we've received another syslog message. The script was smart enough to ignore this message, as it's not a valid start message. So one thing that is not included in the end of the video here, we can still see the host is running clean with very low traffic utilization. The demo doesn't include the message, the stop message, and the withdrawal, but a few minutes after the attack, the Flowspec rules are removed. So one last thing, before we end, I did want to announce that we have open sourced this code. It is on GitHub. You can find it by searching docker-auto-flowspec. And we would love to see others input and contribute and make this better. One of the things that we didn't really enable on this is IPv6. And now there's not a whole lot of IPv6 DDoS attack traffic going on out there, but the future will absolutely have IPv6 DDoS. So maybe that's something that we can all work on and enable that, and we can make this solution even better. Questions?
Hello, John O'Brien, University of Pennsylvania.
Hello.
Nice talk. Thanks very much for doing this work.
Thank you.
I was just wondering, are you aware of the utters service from Team Cymru?
Yes.
Okay, because it seems to me like this would be there's some great sort of opportunity to collaborate and maybe work with those guys to add Flowspec capability to their service, and then maybe offer your tooling to the participants.
Absolutely. Yeah, not just the utters, but the DDoS open threat signaling as well is another project in the IETF that's underway.
Great, thank you.
Thank you.
Hey, Steve Muse from Kentech.
Hey, Ken.
Question, if your DDoS platform supported Flowspec directly, would you rather just use that? Okay.
Yeah, I think in general, a scripted solution like this is great, especially for demonstration, especially for getting that type of awareness into the industry. But in general, we like to have nice vendor-supported software.
Benson Schlieser. I have what is probably a dumb amateur question, but I'm sort of amused by the carpet bombing and wondering if you think that when a carpet bomb happens, they're targeting you and your routers, or just trying to hide and make it harder for you to mitigate the actual target?
That's a great question. I think there's several reasons why they happen. I think one reason may be that the attacker accidentally put a larger subnet in their attack destination, right? But to your point, yeah, I also believe that a lot of those carpet bomb attacks are directly meant to destabilize the ISP infrastructure. Thanks.
Don Smith, CenturyLink.
Hey, Don.
Unwanted traffic removal service, others.
Yes.
I hate hearing. Anyways, it hasn't worked. That is, it hasn't failed, but it's not working either.
Right.
I did reports for months on the advertisements to us as we were part of the group, and I found a couple of large attacks. Most of the time, they were small attacks. They were in the hundreds of megs.
Right.
So people were asking us to destination black hole filter, based on a few hundred megs of traffic they were seeing in their network. Great, I'm going to give them that free service. How do I sell that to management? I couldn't find a way. I'm not saying it failed. I can't sell that.
Absolutely.
So I'm not declaring others dead. I'm just saying it was an attempt to do something that was great in thought and didn't really quite work for us.
Yeah. Thanks, Don.
Hi, Brad Tarno, Rackspace.
Hey, Brian.
In your demo, you have 7 policies, 7 rules for each IP under attack. What happens in a carpet bomb?
That's a
You
great
have
question.
2,000, 3,000 policies.
So that's a great question. So with Flowspec, we could, since it's just like an ACL, we could put, instead of that /32 host, we could put these rules on there for a /16. That would be one way to handle that issue. Now, that actually brings up an interesting question about how much Flowspec rules can a router even take. So I've personally tipped over several routers, just throwing as many Flowspec rules as I possibly could. So again, we run into that question all the time: is can we really off ramp, or can we send 65,000 Flowspec rules to a router? And the answer is no, we can't do that today.
Yeah. How many rules did it take to tip them over?
Oh, well, that depends on the vendor, and that's a good question. So different vendors use different methods for memory.
All right, fair enough. What's the least common denominator?
The least common denominator. Okay, so for large core routers, we find that 10,000 rules is a good number. Thank you. Any other questions? Oh, there you are.
Yeah, KCDCO BYU. Quick question. So let's assume that you have a recursive DNS resolver that is in that address space. So what happens if your rules are dropping packets from source port 53?
I'm glad you asked. So, and again, this is kind of why I put that in there in bold, because I want people to get triggered by this, right? Essentially, if you are blocking UDP source port 53, you will not be able to run a DNS server at your home, essentially, right? Another thing to consider too is how much DNS source port 53 traffic is actually legitimate, and how much would you like coming to your network? You know, so in general, I think that you're going to have people on both sides that say, well, please don't block my UDP 53, and you'll have people that say, please take all of the bad traffic off of my network, and you can't please everyone.
Yeah, I mean, it all depends on the nature of the network and how you have it architected and so forth.
Right. All right. I think that's all. Thank you.